the universe does not behave like a simple empty space filled with objects. At its most fundamental level, modern physics describes reality as a structured system built from fields, geometry, and quantum interactions that operate according to precise mathematical laws tested across decades of experiments. What we casually call nothing is, in physics, anything but empty. Even a perfect vacuum contains fluctuating energy, field activity, and measurable effects that reveal a deep underlying structure. In quantum field theory, every fundamental particle is understood not as a tiny isolated object but as an excitation of an underlying field that exists everywhere in space. The electron field, photon field, quark fields, and Higgs field are always present, even in regions with no detectable matter. When energy is added to these fields, localized excitations appear, which we observe as particles. This framework has been confirmed through high-energy experiments such as those conducted at CERN's Large Hadron Collider, where particle collisions recreate early universe conditions and consistently match predictions made by quantum field equations. One of the most direct pieces of evidence that empty space is physically active is the Casimir effect. When two uncharged metal plates are placed extremely close together in a vacuum, they experience a measurable attractive force. This occurs because quantum fluctuations of the vacuum are restricted between the plates, altering energy density. The result is a pressure difference pushing the plates together. This phenomenon has been experimentally verified with high precision and demonstrates that the vacuum is not empty but filled with real physical processes governed by quantum mechanics. These quantum fluctuations are not random in a meaningless sense. They follow strict probabilistic rules defined by the uncertainty principle, which states that certain pairs of physical quantities, such as energy and time, cannot both be precisely defined at the same moment. This allows temporary violations of energy conservation at extremely small scales, as long as they occur within allowed time intervals. These short-lived fluctuations can produce virtual particle pairs that appear and annihilate almost instantly, but their effects accumulate and become physically significant under certain conditions. When extended to cosmology, these same principles lead to one of the most important ideas in modern theoretical physics, the possibility that the universe itself originated from a quantum fluctuation. In inflationary cosmology, the early universe underwent a period of extremely rapid expansion, driven by a high-energy vacuum state known as the inflaton field. During this phase, space expanded faster than the speed of light, not because objects moved through space, but because space itself expanded. Evidence for inflation comes from precise measurements of the cosmic microwave background radiation, the faint thermal afterglow of the early universe. Satellite missions such as COBE, WMAP, and Planck have mapped tiny temperature variations in this radiation. These fluctuations match the statistical predictions of quantum fluctuations stretched across cosmic scales during inflation. The pattern is highly non-random and follows a nearly scale-invariant spectrum, which is one of the strongest confirmations of inflationary theory. This connection between quantum physics and cosmology suggests that the largest structures in the universe originated from the smallest possible fluctuations. Galaxies, galaxy clusters, and cosmic filaments all trace back to microscopic variations in energy density amplified over billions of years by gravitational attraction. Computer simulations using Einstein's general relativity reproduce these large-scale structures with remarkable accuracy, reinforcing the idea that simple physical laws can generate extreme complexity over time. Gravity itself is not a traditional force in modern physics but a geometric property of spacetime. According to general relativity, developed by Albert Einstein, mass and energy curve spacetime, and this curvature determines the motion of objects. Planets orbit stars not because of a pulling force in the classical sense, but because they follow curved paths in warped spacetime geometry. This has been confirmed through observations such as the bending of light around massive objects, known as gravitational lensing, first verified during solar eclipse experiments in the early 20th century and now routinely observed in astrophysics. Black holes represent the most extreme prediction of general relativity. They are regions where spacetime curvature becomes so strong that nothing, not even light, can escape. Observations by the Event Horizon Telescope collaboration have produced the first direct images of a black hole's shadow, matching theoretical predictions with striking accuracy. These objects also reveal deep connections between gravity, thermodynamics, and quantum theory, particularly through phenomena like Hawking radiation, which suggests that black holes slowly emit particles and lose mass over time. On cosmic scales, the universe is not static but expanding. This was first discovered by Edwin Hubble through observations showing that distant galaxies are moving away from us, with their light shifted toward longer wavelengths, a phenomenon known as redshift. The expansion is not happening within space; instead, space itself is stretching. More surprisingly, this expansion is accelerating due to a mysterious component called dark energy. Dark energy accounts for approximately 68% of the total energy content of the universe. Its exact nature remains unknown, but it behaves as a property of spacetime that drives accelerated expansion. Observations of distant supernovae in the late 1990s revealed that the universe's expansion rate is increasing rather than slowing down, which contradicted earlier expectations based on gravity alone. Alongside dark energy, dark matter makes up about 27% of the universe. It does not emit or absorb light but reveals its presence through gravitational effects on galaxies and galaxy clusters. Rotation curves of galaxies, first studied in detail by astronomers like Vera Rubin, show that visible matter alone cannot account for observed motion, requiring additional unseen mass. Only about 5% of the universe consists of ordinary matter, the type that forms stars, planets, and living organisms. This means that most of reality is invisible and interacts with us only through gravity or large-scale cosmic effects. This fact alone fundamentally changes our understanding of existence, suggesting that what we directly perceive is only a small fraction of a much larger hidden structure. Another key discovery in modern physics is quantum entanglement. When two particles become entangled, their properties remain correlated even when separated by vast distances. Experiments testing Bell's inequalities, performed repeatedly since the 1980s and refined by researchers such as Anton Zeilinger, have confirmed that no local hidden variable theory can explain these correlations. This means that information in the universe is not strictly localized in space in the way classical physics would suggest. All of these findings point toward a consistent picture. The universe is not built from solid objects in empty space, but from interacting fields, geometric structures, and information-based relationships governed by mathematical laws. These laws remain consistent across enormous scales, from subatomic particles to the structure of the entire observable cosmos. Whether these laws are fundamental or emergent from a deeper layer of reality is still unknown. But what is clear is that the universe behaves as a unified system where quantum mechanics, relativity, and cosmology are deeply interconnected, forming a framework that continues to reveal new layers of structure the more precisely it is studied. If the first layer of reality is quantum fields and spacetime geometry, the next deeper question in modern physics is why these structures exist in the form they do and whether they could have been different. This leads directly into one of the most important ideas in theoretical cosmology. The laws of physics may not be uniquely fixed, but instead represent one solution among many possible consistent mathematical frameworks. In general relativity, spacetime is described using Einstein's field equations, which relate the curvature of spacetime to the distribution of mass and energy. These equations do not produce a single type of universe. Instead, they allow a wide range of solutions depending on initial conditions, energy density, and geometry. Some solutions describe expanding universes like ours, others describe collapsing universes, and some even describe exotic possibilities such as closed time-like curves under extreme conditions. This mathematical flexibility suggests that the structure of the universe is not forced into one form by necessity, but emerges from a broader space of possibilities. Quantum mechanics adds an even deeper layer of uncertainty and multiplicity. The Schrödinger equation, which governs the evolution of quantum systems, does not predict a single outcome. Instead, it predicts a wave function that contains all possible outcomes with associated probabilities. This is not a limitation of measurement but a fundamental feature confirmed by countless experiments, including double-slit interference tests and precision measurements of atomic behavior. When measurements are made, the system appears to collapse into one outcome, but the underlying mathematics continues to describe a full spectrum of possibilities. This naturally leads to interpretations in which all outcomes exist simultaneously in different branches of reality. One of the most well-known is the many worlds interpretation, originally proposed by Hugh Everett. In this framework, every quantum event causes a branching of the universe into multiple non-communicating histories. While experimentally indistinguishable from other interpretations at present, it is fully consistent with the mathematical structure of quantum mechanics and removes the need for wave function collapse as a special physical process. On a larger scale, cosmology introduces the concept of inflationary space. According to inflation theory, the early universe underwent exponential expansion driven by a high-energy vacuum state. This process is supported by measurements of the cosmic microwave background, which show a nearly flat geometry and a very specific pattern of fluctuations. However, inflation is not necessarily a one-time event. Some models suggest that inflation can continue eternally in different regions of space, producing bubble universes that separate from one another as space expands between them faster than light can bridge the gaps. Each of these bubble universes could, in principle, have different physical constants depending on how symmetry breaking occurred during their formation. Symmetry breaking is a process in particle physics where a highly symmetric state transitions into a lower symmetry state as the universe cools. This is essential in explaining how distinct forces like electromagnetism and the weak nuclear force became separate after the early unified state. The Higgs mechanism is a verified example of symmetry breaking, confirmed through the discovery of the Higgs boson at CERN in 2012. If symmetry breaking occurred differently in other regions of a larger inflationary system, the resulting universes could have entirely different particle masses, force strengths, or even dimensional structures. Some might not form stable atoms, while others could have radically different chemistry or no long-lived stars. This idea is not speculative in the sense of violating known physics. It emerges directly from equations used in modern particle physics and cosmology. Another important framework is string theory, which attempts to unify quantum mechanics and gravity. In string theory, fundamental particles are not point-like but instead one-dimensional vibrating strings. The different vibrational modes of these strings correspond to different particles. However, string theory does not predict a single unique vacuum state. Instead, it allows an enormous number of possible solutions, often referred to as the string landscape. Estimates suggest there could be as many as 10 to the power of 500 possible vacuum configurations, each corresponding to a different possible universe with its own physical laws. This vast landscape implies that what we call our universe may be one configuration among an almost unimaginable number of mathematically consistent possibilities. Each configuration is governed by the same underlying principles but produces different observable physics depending on how dimensions are compactified and how fields settle into stable states. At the same time, observations of our own universe reveal a surprising feature: it appears finely balanced for complexity. Small changes in fundamental constants would drastically alter the formation of matter. For example, if the strength of the strong nuclear force were slightly different, atomic nuclei would either not bind or would fuse too easily, preventing stable chemistry. If the electromagnetic force were significantly stronger or weaker, electron orbitals would not support stable atoms. These sensitivities have led to what is known as the fine-tuning problem in physics. One explanation for this is selection bias in a multiverse. If many universes exist with varying constants, only those capable of supporting complex structures and observers would be observed. This reasoning is known as the anthropic principle. It does not explain why the multiverse exists, but it provides a statistical explanation for why we find ourselves in a universe with life-permitting conditions. Observational cosmology also reveals that the universe is expanding at an accelerating rate. This was discovered through Type Ia supernova measurements in distant galaxies, which showed that light from these explosions was dimmer than expected, indicating that space has expanded more rapidly over time. The cause of this acceleration is attributed to dark energy, which behaves like a constant energy density filling space uniformly. The simplest model of dark energy is the cosmological constant, originally introduced by Einstein and later reinterpreted after the discovery of expansion. The presence of dark energy leads to a long-term prediction: the observable universe will continue expanding, causing distant galaxies to move beyond our cosmic horizon. Over extremely long time scales, this leads to a scenario in which only gravitationally bound systems remain visible, such as local galaxy clusters, while the rest of the universe becomes inaccessible due to the expansion of space. Dark matter, on the other hand, influences structure formation on galactic scales. It does not interact with light but exerts gravitational influence that shapes galaxy rotation curves and large-scale cosmic structure. Numerical simulations of structure formation show that without dark matter, galaxies would not form in the observed way. Its existence is supported by multiple independent lines of evidence, including gravitational lensing, cosmic microwave background data, and galaxy cluster dynamics. Together, dark matter and dark energy dominate the total energy content of the universe, yet neither is directly understood in terms of fundamental particles within the Standard Model. This suggests that current physics may be incomplete, pointing toward deeper layers of reality not yet fully described. At the same time, quantum entanglement continues to challenge classical intuitions about space and locality. Experiments testing Bell inequalities show that entangled particles exhibit correlations that cannot be explained by any local hidden variables. These results have been confirmed repeatedly under increasingly strict experimental conditions, including loophole-free Bell tests. This implies that the universe cannot be fully described by local classical realism alone, and that information plays a non-local role in the structure of reality. When combined, these ideas suggest a picture of the universe as a system defined not by fixed objects in space, but by interacting fields, probabilistic outcomes, geometric curvature, and informational relationships. The deeper structure of reality appears to be governed by consistent mathematical frameworks that allow for multiple possible configurations, some of which we may never directly observe but which remain valid solutions within the same underlying physical laws. When cosmology is pushed beyond the observable universe, physics begins to describe not just what exists, but what could exist under the same mathematical laws. This shift is important because modern equations do not single out one unique universe. Instead, they allow entire families of solutions, each internally consistent but potentially radically different in structure, constants, and evolution. One of the strongest theoretical motivations for this comes from inflationary cosmology. During inflation, space expanded exponentially fast due to a high-energy vacuum state. This process is described by scalar field dynamics, often modeled through an inflaton field rolling down a potential energy landscape. The exact shape of this potential determines how inflation ends locally, but in many models inflation never ends everywhere at once. Instead, it continues in some regions while stopping in others. This creates a self-reproducing spacetime structure often called eternal inflation. In eternal inflation, bubble universes form when inflation stops in a localized region, allowing matter and radiation to form while surrounding space continues inflating. These bubbles are causally disconnected, meaning no signal traveling at or below the speed of light can cross between them once separation occurs. Each bubble universe can therefore evolve independently, effectively becoming its own universe with its own observable laws. This mechanism is not speculative fiction but arises naturally in multiple inflationary models consistent with current cosmological data. Measurements of the cosmic microwave background support the inflationary framework by showing that the universe is extremely close to spatially flat on large scales. The Planck satellite data also shows that primordial fluctuations follow a nearly Gaussian distribution with a specific spectral index slightly below 1, exactly as predicted by simple inflation models. These observations do not prove eternal inflation, but they make inflation itself one of the most strongly supported theories in modern cosmology. At the same time, particle physics suggests that the vacuum state of our universe may not be unique or permanently stable. The Higgs field, discovered through the Higgs boson at CERN, gives particles mass through interaction with a non-zero vacuum expectation value. Calculations based on measured Higgs and top quark masses suggest that the current vacuum could be metastable, meaning it is stable for extremely long times but not necessarily the lowest possible energy state. If true, this implies that more stable vacuum states could exist, and transitions between them would fundamentally alter the laws of physics in a given region of spacetime. This idea connects directly to the concept of vacuum decay, where quantum tunneling could cause a region of space to transition to a lower energy state. Such an event would propagate at near light speed, completely changing particle masses and force strengths in its path. While there is no evidence that this has ever occurred, it is a mathematically allowed outcome in quantum field theory. Another important structure in modern physics is the concept of gauge symmetry. The standard model of particle physics is built on gauge groups such as SU3, SU2, and U1, which define how fundamental particles interact. These symmetries determine the existence of forces like the strong nuclear force, weak nuclear force, and electromagnetism. What is crucial is that these symmetry groups are not uniquely required by logic alone, they are selected based on consistency with observed particle behavior. Other symmetry groups are mathematically valid and could describe alternative physical systems, even if they do not correspond to our universe. This opens the door to the idea that different symmetry breakings in different regions of a larger cosmological structure could produce entirely different physics. In some regions, electromagnetism might not exist as we know it. In others, stable atoms might never form. In yet others, space itself might have different numbers of dimensions or different curvature properties. These possibilities emerge directly from known mathematical frameworks in quantum field theory and string-inspired models. String theory extends this idea further by proposing that particles are not point-like but are vibrating one-dimensional objects. The vibrational modes determine particle properties such as mass and charge. However, string theory requires extra spatial dimensions beyond the familiar three. These additional dimensions are thought to be compactified into extremely small geometric shapes, known as Calabi-Yau manifolds. The way these dimensions are compactified determines the effective physical laws in lower dimensions. The major implication of string theory is that there is not a single predicted vacuum state but an enormous landscape of possible vacua. Each vacuum corresponds to a different way of compactifying dimensions and stabilizing fields. This leads to a vast number of mathematically consistent universes, each with different constants and particle content. While no direct experimental evidence currently confirms string theory, its mathematical consistency with quantum mechanics and gravity makes it a major candidate for a unified theory. On observational scales, another striking feature of the universe is its large-scale structure. Galaxies are not randomly distributed but form a cosmic web composed of filaments, clusters, and voids. This structure emerged from small primordial density fluctuations amplified by gravity over billions of years. Simulations using supercomputers show that dark matter plays a crucial role in forming this web by providing gravitational scaffolding around which normal matter accumulates. Gravitational lensing provides direct evidence for this structure. When light from distant galaxies passes near massive objects, its path is bent due to spacetime curvature. Observations of lensing patterns allow scientists to map dark matter distribution even though it cannot be seen directly. These maps consistently show that visible matter is only a small part of the total gravitational structure of the universe. Another important discovery is the isotropy and homogeneity of the universe on very large scales, often referred to as the cosmological principle. While local regions contain complex structures like galaxies and clusters, when averaged over hundreds of millions of light-years, the universe appears statistically uniform in all directions. This property is crucial for applying cosmological models based on general relativity. However, there are also anomalies in cosmic observations that continue to be studied. Certain large-scale alignments in the cosmic microwave background, sometimes referred to as the axis of evil, have sparked debate about whether unknown physical processes or statistical variations might be involved. While not yet conclusive, these anomalies highlight that cosmology is still an active field with open questions. Quantum entanglement also raises deeper questions about the nature of spacetime itself. Some approaches to quantum gravity suggest that spacetime geometry may emerge from patterns of quantum entanglement. In these models, space is not fundamental but arises from the connectivity of quantum information. This idea is supported by developments in holographic duality, particularly the ADS/CFT correspondence, which shows that a gravitational theory in a volume can be mathematically equivalent to a quantum theory on its boundary. This holographic principle suggests that the information content of a region of space may be encoded on its surface area rather than its volume. Black hole thermodynamics supports this idea, as the entropy of a black hole is proportional to the area of its event horizon, not its volume. This leads to the radical possibility that the universe itself may be describable as a lower-dimensional informational system. Taken together, inflation, quantum field theory, symmetry breaking, string landscapes, and holographic principles all point toward a view of reality in which the universe is not a single fixed structure but a dynamically generated outcome of deeper mathematical rules. These rules allow for multiple consistent configurations, some of which may exist beyond our observational reach but remain valid within the same theoretical framework. As cosmology extends beyond direct observation, it increasingly relies on mathematical consistency rather than visual confirmation. One of the most important consequences of this shift is the idea that spacetime itself may not be fundamental. Instead, spacetime could emerge from deeper quantum structures that are not spatial or temporal in nature at all. In classical physics, space and time are treated as a continuous stage on which events unfold. However, general relativity already changes this picture by showing that spacetime is dynamic and influenced by matter and energy. Quantum mechanics pushes this further by showing that at extremely small scales, continuity may break down. Many approaches to quantum gravity suggest that spacetime is not smooth but composed of discrete or relational units that only appear continuous at large scales. One of the strongest theoretical frameworks exploring this idea is loop quantum gravity. In this model, space is quantized, meaning it has a smallest possible unit of structure. Instead of being infinitely divisible, areas and volumes come in discrete chunks. These are described using mathematical objects called spin networks, which evolve over time into spin foams. This suggests that geometry itself is built from underlying quantum relationships rather than existing as a continuous background. Another approach comes from causal set theory, which proposes that spacetime is fundamentally a discrete set of events ordered by causality. In this view, the universe is not made of space filled with objects, but of events connected by cause and effect relationships. Geometry emerges only when large numbers of these events are combined, producing the smooth spacetime we observe at macroscopic scales. These ideas align with the broader trend in theoretical physics where information becomes a central concept. In black hole physics, this is especially important. The black hole information paradox arises from the question of what happens to information that falls into a black hole. Classical general relativity suggests it is lost, while quantum mechanics forbids information loss. This contradiction led to major developments in theoretical physics, including Hawking radiation and the holographic principle. Hawking radiation shows that black holes are not completely black but slowly emit particles due to quantum effects near the event horizon. Over extremely long time scales, this leads to black hole evaporation. The key question is whether the information about what fell into the black hole is destroyed or encoded in some subtle way in the outgoing radiation. Most modern approaches suggest that information is preserved, although in a highly scrambled form. The holographic principle, developed through studies of black hole entropy, suggests that all information contained within a volume of space can be described by information encoded on its boundary surface. This idea was made precise in string theory through the ADS/CFT correspondence, discovered by Juan Meldacena, which shows that a gravitational theory in a higher dimensional space can be equivalent to a quantum field theory without gravity on its lower dimensional boundary. This duality is one of the strongest hints that gravity and spacetime may be emergent phenomena. If spacetime is emergent, then the question of the universe's origin becomes more subtle. Instead of asking what happened before the universe, we may need to ask what underlying structure gives rise to spacetime itself. In several quantum gravity approaches, time is not fundamental but arises from correlations between quantum states. This challenges the traditional notion of a single initial moment in time. Cosmological models based on quantum tunneling also suggest that universes can form spontaneously from metastable quantum states. In these models, a universe can appear when a system transitions from a higher energy false vacuum to a lower energy configuration. This process does not require external input but is governed entirely by probabilistic quantum laws. While highly theoretical, these models are mathematically consistent with quantum field theory. Another important area of study is the arrow of time. Physical laws at the microscopic level are mostly time-symmetric, meaning they work the same forward and backward in time. However, macroscopic reality shows a clear direction of time, characterized by increasing entropy. This is described by the second law of thermodynamics. The reason for this asymmetry is still an active area of research, but it is often linked to the low entropy conditions of the early universe. Measurements of the cosmic microwave background suggest that the early universe was in a highly ordered state despite being extremely hot and dense. As it expanded, entropy increased, allowing structures such as stars, galaxies, and eventually life to form. This thermodynamic evolution is one of the key reasons why time appears to flow in a single direction. In addition to time and space, modern physics increasingly treats information as a fundamental quantity. John Wheeler's concept of it from bit proposes that physical reality ultimately arises from binary informational choices. In quantum mechanics, measurement outcomes are fundamentally probabilistic, and the act of measurement plays a central role in defining physical states. This suggests that information is not just descriptive but potentially constitutive of reality itself. Experimental quantum computing research also supports the idea that information behaves in fundamentally physical ways. Quantum bits, or qubits, can exist in superposition states and become entangled across distances, allowing computational processes that have no classical equivalent. These systems demonstrate that information in quantum systems is deeply linked to physical laws rather than being an abstract concept. At cosmic scales, the distribution of matter also reflects underlying information encoded in the early universe. The pattern of galaxies and voids observed today corresponds to initial quantum fluctuations stretched by inflation. This means that the large-scale structure of the universe can be traced back to probabilistic information encoded in its earliest moments. There is also growing interest in whether spacetime itself can be reconstructed from entanglement patterns. In certain theoretical models, the connectivity of space emerges from the strength and structure of quantum entanglement between underlying degrees of freedom. Strongly entangled systems correspond to closely connected regions of spacetime, while weakly entangled systems correspond to distant or disconnected regions. This suggests that geometry may be a secondary effect of quantum correlations. If this is correct, then the universe is fundamentally relational rather than object-based. Instead of objects existing in space, space itself is a manifestation of relationships between underlying quantum states. This reverses the classical picture of reality and replaces it with a network-like structure where geometry, matter, and information are inseparable. Taken together, these ideas suggest that the universe may be far more abstract than everyday intuition suggests. Space, time, and matter may all emerge from a deeper informational and mathematical structure that operates according to consistent but non-classical principles. While still theoretical, these frameworks are increasingly constrained by observational data and mathematical consistency, making them serious candidates for describing the deepest layers of reality. Black holes are not just exotic objects in space, they are where our current understanding of physics starts to break in the most fundamental way. They emerge naturally from general relativity, the theory that describes gravity not as a force, but as the bending of spacetime caused by mass and energy. When a sufficiently massive star collapses under its own gravity after exhausting nuclear fuel, no known force can stop the collapse beyond a certain point. What remains is a region where spacetime curvature becomes so extreme that escape becomes impossible. That boundary is called the event horizon. The event horizon is not a physical surface you could touch or land on. It is a mathematical boundary defined by the escape velocity reaching the speed of light. Once matter or radiation crosses it, all possible paths forward in time lead deeper into the black hole. This is not a matter of speed or propulsion but geometry itself. Space and time inside that region are so distorted that moving outward becomes as impossible as reversing time in normal conditions. The first mathematical description of this phenomenon came from Karl Schwarzschild in 1916, shortly after Einstein published general relativity. He solved Einstein's equations for a simple case, a non-rotating, spherically symmetric mass. The result was the Schwarzschild radius, the size at which an object of a given mass becomes a black hole. For Earth, this radius is about 9 millimeters. Compress the entire planet into a sphere that small, and it would become a black hole. For decades, black holes remained a theoretical curiosity. Many physicists, including Einstein himself, were skeptical that nature would allow such extreme objects to form. However, as stellar evolution theory developed, it became clear that massive stars naturally end their lives in gravitational collapse. When a star much larger than the Sun exhausts its nuclear fuel, it no longer has the outward pressure needed to balance gravity. The core collapses, and depending on mass, it becomes a white dwarf, neutron star, or black hole. Today, we have overwhelming observational evidence that black holes exist. One of the most direct confirmations came from the detection of gravitational waves by the LIGO Observatory. These waves are ripples in spacetime itself, predicted by general relativity. In 2015, LIGO detected a signal from two merging black holes more than 1 billion light-years away. The waveform matched theoretical predictions with extreme precision, confirming that black holes not only exist but also collide and merge in the universe. Another milestone came from the Event Horizon Telescope, which produced the first image of a black hole's shadow in the galaxy M87. What we see is not the black hole itself, which emits no light, but the glowing accretion disk of superheated plasma orbiting it. The dark central region is the shadow cast by the event horizon, bending and capturing light through gravitational lensing. The shape and size of this shadow matched predictions from Einstein's equations, providing strong confirmation of the theory. At the center of most large galaxies, including our own Milky Way, lies a supermassive black hole. Ours is called Sagittarius A star. It has a mass about 4 million times that of the Sun's stars near the center of the galaxy orbit at extremely high speeds around an invisible point, providing indirect but powerful evidence of this massive compact object. These supermassive black holes likely formed early in cosmic history and grew alongside their galaxies. Despite their name, black holes are not entirely black in a theoretical sense. In the 1970s, Stephen Hawking discovered that quantum effects near the event horizon cause black holes to emit faint radiation. This phenomenon, known as Hawking radiation, arises because quantum fluctuations constantly create particle-antiparticle pairs even in vacuum. Near the event horizon, one particle can fall in while the other escapes, making it appear as if the black hole is slowly emitting radiation. This leads to one of the deepest unresolved problems in physics, the information paradox. According to quantum theory, information about a physical system cannot be destroyed. However, if a black hole evaporates completely through Hawking radiation, what happens to the information about everything that fell inside it? Is it lost forever, or somehow preserved in the radiation? This question connects directly to quantum mechanics and the nature of reality itself. If information is truly lost, it would violate fundamental principles of quantum theory. Many physicists believe instead that information is preserved, but in a highly scrambled form encoded in the radiation or at the event horizon itself. This idea led to one of the most revolutionary concepts in modern theoretical physics, the holographic principle. It suggests that all information contained in a volume of space can be described by information encoded on its boundary surface. In other words, the three-dimensional world might be a projection of two-dimensional data. This idea emerged from studying black hole entropy. Jacob Bekenstein showed that black holes have entropy proportional to the area of their event horizon, not their volume. This was unexpected because entropy in normal systems scales with volume. This area scaling hinted that the true number of fundamental degrees of freedom in a region of space might be limited by its boundary, not its interior. The holographic principle is not just philosophical speculation, it is supported by mathematical frameworks such as string theory and the ADS/CFT correspondence. In these models, a gravitational system in a higher dimensional space can be exactly equivalent to a quantum field theory without gravity in lower dimensions. This duality suggests that spacetime and gravity may be emergent phenomena rather than fundamental components of reality. Black holes also play a central role in shaping cosmic structure. When matter falls into a black hole, it forms an accretion disk, heating up due to friction and magnetic forces. Some of this matter is not swallowed but instead ejected in the form of relativistic jets. These jets can extend for thousands of light years, carrying enormous amounts of energy into intergalactic space. These processes influence galaxy evolution. Supermassive black holes can regulate star formation by heating surrounding gas, preventing it from collapsing into new stars. This feedback mechanism helps explain why galaxies have the shapes and sizes we observe. Without black holes, the structure of the universe would likely be very different. There are also theoretical ideas suggesting that black holes may connect to other regions of spacetime through structures known as wormholes. While solutions to Einstein's equations allow for such geometries, they are likely unstable and would collapse before anything could pass through. Still, they highlight how general relativity permits far stranger possibilities than everyday intuition suggests. Another deep idea is that spacetime itself might emerge from quantum entanglement. In some modern approaches to quantum gravity, the connectivity of spacetime is linked to how particles are entangled. If entanglement is reduced, spacetime geometry can tear apart. This suggests that the smooth fabric of space may be a large-scale manifestation of microscopic quantum information patterns. Black holes also challenge our understanding of time. Near the event horizon, time dilation becomes extreme. To a distant observer, an object falling into a black hole appears to slow down and freeze at the horizon, never quite crossing it. From the perspective of the falling object, however, it crosses the horizon in finite time without noticing anything special at that moment. This difference highlights the relativity of time itself. In strong gravitational fields, time is not universal but depends on position and motion. Black holes represent the most extreme environment where these effects dominate completely. Ultimately, black holes are not just astrophysical objects. They are laboratories where gravity, quantum mechanics, thermodynamics, and information theory collide. They force us to confront the limits of current physics and suggest that spacetime, matter, and information may not be separate entities but different expressions of a deeper underlying structure. Understanding them fully may require a new theory that unifies all fundamental forces, revealing what reality is made of at its most basic level. If black holes expose the limits of gravity and quantum theory, then dark energy exposes the limits of cosmology itself. It is one of the most mysterious components of the universe, and unlike anything in everyday experience. Observations of distant supernovae in the late 1990s revealed something unexpected. The expansion of the universe is not slowing down under gravity, but accelerating. This discovery completely changed modern cosmology and introduced the idea of a dominant, invisible energy filling space. This phenomenon is currently described within the framework of Lambda CDM model, where lambda represents the cosmological constant introduced by Einstein. Originally, Einstein added this constant to keep the universe static, but later called it his greatest mistake after the discovery of cosmic expansion. Ironically, modern measurements suggest that this constant-like term may actually be real. Dark energy is not a substance in the traditional sense. It does not clump, shine, or interact with light. Instead, it behaves as a property of spacetime itself. Every cubic meter of empty space appears to contain a small but non-zero amount of energy. As space expands, more of this energy appears, causing the expansion to accelerate further. This leads to a runaway effect where expansion feeds itself. The most precise measurements of dark energy come from multiple independent sources: Type Ia supernovae, the cosmic microwave background, and large-scale structure surveys. These all converge on a consistent picture, Roughly 68 to 70% of the total energy content of the universe is dark energy, about 25 to 27% is dark matter, and only about 5% is ordinary matter. This means everything we see, stars, planets, galaxies, is a tiny fraction of reality. Dark matter itself is still invisible, but it is inferred through gravitational effects. Galaxies rotate too fast to be held together by visible matter alone, and galaxy clusters behave as if they contain far more mass than we can detect. Dark matter provides the missing gravitational glue. However, dark energy is the opposite problem. Instead of pulling structures together, it pushes the universe apart. One of the simplest ways to describe dark energy mathematically is through Einstein's field equations of general relativity, where an additional term lambda, represents vacuum energy density. If lambda is positive, spacetime itself has a built-in tendency to expand. This expansion is not motion through space, but expansion of space itself. Distances between galaxies increase even if nothing locally moves. The key observational evidence for this accelerated expansion comes from redshift measurements. Distant galaxies show that their light is stretched toward longer wavelengths, meaning they are moving away from us. But more importantly, distant supernovae appear dimmer than expected in a decelerating universe, indicating that expansion has been speeding up over time. One of the biggest questions is why vacuum energy exists at all. Quantum field theory suggests that even empty space is filled with fluctuating fields due to the uncertainty principle. These fluctuations contribute energy, but theoretical predictions are wildly off compared to observed values, by a factor of about 10 superscript 1 superscript 2, one of the largest discrepancies in physics. This is known as the cosmological constant problem. This mismatch suggests that either our understanding of quantum vacuum energy is incomplete, or some cancellation mechanism exists that we do not yet understand. Many physicists suspect that a deeper theory of quantum gravity may resolve this, potentially linking dark energy to the structure of spacetime at the smallest scales. Some theories propose that dark energy is not constant at all, but dynamic. These models are called quintessence models, where a slowly evolving field changes over time and drives cosmic acceleration. If true, the rate of expansion could vary in the future, possibly slowing, stabilizing, or even reversing depending on the field's evolution. The long-term consequences of dark energy are profound. If acceleration continues indefinitely, galaxies outside our local group will eventually move beyond the observable horizon. Over trillions of years, the universe could become isolated islands of gravitationally bound structures surrounded by an expanding void. Future observers might see only their own galaxy, with no evidence of the wider cosmos. This leads to a concept sometimes called the Big Freeze, or heat death, where the universe continues expanding until stars burn out, black holes dominate, and entropy reaches a maximum state. In this scenario, structure gradually disappears not through collapse, but through dilution. However, dark energy may also connect to deeper properties of spacetime. In some interpretations of quantum gravity, vacuum energy is linked to the geometry of higher dimensional space. For example, in string theory frameworks, what we perceive as dark energy might arise from how extra dimensions are compactified or stabilized. There is also a connection between dark energy and the holographic principle. If spacetime is emergent from information encoded on boundaries, then dark energy could represent an effective pressure arising from information constraints at cosmic horizons. This idea remains speculative, but it highlights how cosmology, quantum theory, and information theory are increasingly intertwined. Observational cosmology continues to refine measurements of dark energy through projects like the Dark Energy Survey and Euclid mission. These aim to map the large-scale structure of the universe with unprecedented precision, tracking how galaxies cluster over billions of years. Small deviations from expected patterns could reveal whether dark energy is truly constant or evolving. Another intriguing aspect is the possibility that dark energy is related to the energy of the vacuum state itself. In quantum field theory, each field has a lowest energy configuration. If the universe is not in the absolute lowest possible vacuum state, it could be in a metastable state, meaning a higher energy configuration that could eventually decay. If such a vacuum decay occurred, it would fundamentally alter the laws of physics in a region of space, propagating at near light speed. This is purely theoretical, but it shows that dark energy may be connected to the stability of reality itself. Despite its dominance, dark energy remains completely undetected in laboratory experiments. We only observe its effects on cosmic scales. This makes it one of the most indirect yet powerful components in physics, something that shapes the entire universe while remaining invisible in every experiment we can currently perform. In a broader sense, dark energy forces a shift in how we think about nothingness. Empty space is not empty. It has structure, energy, and dynamics. The vacuum is not a void but an active component of the universe. This changes the philosophical picture of reality. Space itself becomes a physical entity with properties, evolution, and influence. When combined with dark matter, black holes, and quantum mechanics, a consistent picture begins to emerge where the universe is not made of isolated objects but interacting fields and information structures. Matter is just one expression of deeper underlying physics, while space and time themselves may be emergent phenomena. Dark energy remains one of the greatest unresolved mysteries in science. It defines the fate of the universe on the largest scales, yet its origin is still unknown. Whether it is a constant of nature, a dynamic field, or a manifestation of deeper quantum structure, solving it will likely require a new level of physics beyond both general relativity and quantum mechanics. Until then, it stands as a silent driver of cosmic evolution, stretching the universe ever outward, shaping its future in ways we can observe but not yet fully understand. Beyond black holes and dark energy, the deepest mystery in modern physics is not a single object or force, but the structure of reality itself. At the smallest scales, the universe does not behave like a smooth, continuous fabric. Instead, it behaves like something granular, probabilistic, and fundamentally uncertain. This is the domain of quantum mechanics, where particles do not have definite positions or velocities until they are measured, and where reality is described by probabilities rather than certainties. At the core of quantum theory is the wave function, a mathematical object that encodes all possible outcomes of a system. Before observation, a particle exists in a superposition of states, meaning it is not in one place or one state but in many possibilities simultaneously. Only when a measurement occurs does this superposition appear to collapse into a definite outcome. This raises a fundamental question: what counts as a measurement, and why does observation play such a central role in physical reality? Experiments consistently confirm quantum predictions with extreme precision. The double-slit experiment, one of the most famous demonstrations, shows that particles like electrons behave like waves when not observed, producing interference patterns. However, when measured, they behave like discrete particles. This dual behavior is not an illusion, it is a fundamental feature of nature. One of the most important consequences of quantum theory is uncertainty. The Heisenberg uncertainty principle states that certain pairs of physical properties, such as position and momentum, cannot both be known precisely at the same time. This is not due to measurement errors, but a fundamental limit built into reality itself. The more precisely one property is known, the less precise the other becomes. At first glance, quantum mechanics seems disconnected from the large-scale universe. However, it is deeply connected to cosmology. The early universe, immediately after the Big Bang, was governed by quantum fluctuations. Tiny random variations in energy density were stretched by cosmic inflation into the seeds of galaxies, stars, and all large-scale structures we see today. Without quantum randomness, the universe would likely be perfectly uniform and structurally empty. Quantum fields are now understood as the fundamental entities of nature. Particles are not independent objects but excitations of underlying fields that fill all of space. Every electron is an excitation of the electron field, every photon of the electromagnetic field, and so on. This means that empty space is actually filled with fields constantly fluctuating at the quantum level. These fluctuations are not just theoretical. They produce measurable effects such as the Casimir effect, where two uncharged metal plates placed extremely close together experience an attractive force due to changes in vacuum energy between them. This demonstrates that the quantum vacuum is physically real and has measurable consequences. Another major feature of quantum theory is entanglement. When two particles interact, they can become linked in such a way that their properties remain correlated even when separated by vast distances. Measuring one particle instantly determines the state of the other, regardless of distance. This phenomenon was once called spooky action at a distance by Einstein, and it remains one of the most counterintuitive aspects of physics. Entanglement is not just a curiosity, it is now understood as a key resource in quantum computing and quantum information theory. It suggests that information, rather than matter or energy, may be the most fundamental building block of reality. In some modern approaches to quantum gravity, spacetime itself may emerge from patterns of entanglement between underlying quantum states. This idea connects directly to the holographic principle, where the information contained in a region of space is encoded on its boundary. If true, this means that the three-dimensional world we experience could be a projection of two-dimensional quantum information. This radically changes the meaning of space and dimension. Another unresolved issue in quantum mechanics is the measurement problem. The theory describes probabilities extremely well, but it does not clearly explain why or how a single outcome is chosen during observation. Several interpretations exist. The Copenhagen interpretation suggests that observation causes collapse. The many worlds interpretation suggests that all outcomes occur, each in a separate branching universe. Other interpretations involve hidden variables or objective collapse mechanisms. The many worlds interpretation connects directly to cosmology. If every quantum event branches reality, then the universe is constantly splitting into an enormous tree of parallel histories. Each branch evolves independently, forming a vast multiverse structure. In this view, what we call reality is just one path through an infinite quantum branching system. Quantum mechanics also introduces limits to predictability. Even with perfect knowledge of a system's initial conditions, only probabilities of outcomes can be calculated. This is fundamentally different from classical physics, where future states are fully determined by initial conditions. In quantum theory, randomness is built into the fabric of reality. Despite its success, quantum mechanics is incomplete when it comes to gravity. Gravity is described by general relativity, which treats spacetime as smooth and continuous. Quantum theory, on the other hand, treats nature as discrete and probabilistic. These two frameworks work extremely well in their own domains but break down when combined, such as inside black holes or at the origin of the universe. This conflict is one of the biggest unsolved problems in physics. A unified theory of quantum gravity is expected to reconcile these frameworks, possibly revealing that spacetime itself is not fundamental but emergent from deeper quantum structures. Some approaches, such as loop quantum gravity, suggest that spacetime is composed of discrete units called quanta of space. Others, like string theory, propose that fundamental particles are not points but tiny vibrating strings existing in higher dimensional space. Both approaches aim to describe a deeper layer of reality where space, time, and matter arise from more fundamental principles. Quantum theory also has deep implications for causality. In classical physics, cause always precedes effect. However, in quantum systems, events can be correlated in ways that do not fit simple temporal ordering. Some experiments suggest that the distinction between past and future may not be as absolute as it appears at macroscopic scales. On the cosmological level, quantum fluctuations may even determine the structure of the entire universe. Inflation theory suggests that the observable universe originated from a tiny quantum region that expanded exponentially. This means that the large-scale structure of galaxies is ultimately rooted in microscopic randomness. Quantum physics also raises philosophical questions about reality itself. If observation plays a role in determining outcomes, then what is the status of reality without observers? Does the universe exist in a definite state, or only as a network of potentialities? These questions remain open and deeply debated. What is clear is that quantum mechanics does not describe a simple, deterministic universe. Instead, it describes a reality built on probability, interaction, and information. Particles are not isolated objects but interconnected excitations of fields, and spacetime itself may emerge from deeper quantum relationships. As research continues, quantum theory is increasingly seen not as a complete description of particles, but as a window into a deeper structure of reality. Whether through entanglement, holography, or quantum gravity, the goal is the same: to understand what lies beneath the apparent randomness of the universe and whether that randomness is truly fundamental or just a feature of a deeper deterministic structure we have not yet discovered. If quantum mechanics reveals that reality behaves unpredictably at small scales, then cosmology reveals something even stranger: the universe itself has a history that begins in conditions where our current laws of physics stopped working. The earliest moments of existence are described by models of extreme density and temperature, where spacetime itself was compressed into a state that cannot be fully described by any tested theory. This is the domain of the early universe, where all known forces may have once been unified into a single framework before separating into the distinct interactions we observe today. According to the standard cosmological framework, the universe expanded from an extremely hot and dense initial state in what is commonly called the Big Bang. However, this is not an explosion in space, but an expansion of space itself. Every region of the universe was once much closer together, and as expansion continues, galaxies are carried apart not because they move through space, but because space itself stretches. This distinction is critical to modern cosmology and is fully consistent with general relativity. One of the strongest pieces of evidence for this early hot state is the cosmic microwave background radiation. This is faint radiation filling the entire universe, observed in every direction, and it represents the leftover thermal glow from when the universe first became transparent. Before this moment, the universe was a dense plasma of photons, electrons, and baryons, constantly scattering light. As expansion cooled the universe enough for neutral atoms to form, light was finally able to travel freely. That ancient light has now been stretched into microwave wavelengths due to cosmic expansion. Measurements of the cosmic microwave background show tiny fluctuations in temperature, on the order of 1 part in 100,000. These fluctuations are extremely important because they represent the seeds of all future structure in the universe. Over time, gravity amplified these small variations into galaxies, clusters, and the cosmic web. Without these fluctuations, the universe would likely remain featureless and structureless. The origin of these fluctuations is believed to come from quantum processes. During a brief period called cosmic inflation, the universe is thought to have expanded exponentially fast, driven by a high-energy field. In this period, quantum fluctuations were stretched across cosmic scales, freezing into density variations. This connects the smallest scales of physics directly to the largest structures in the universe. Inflation theory also helps explain why the universe appears so uniform on large scales. Regions of space that are now far apart were once close enough to reach thermal equilibrium before inflation stretched them beyond causal contact. This solves the so-called horizon problem, one of the major puzzles in early cosmology. Another major puzzle is the flatness problem. Observations show that the universe is extremely close to geometrically flat on large scales. In general relativity, curvature depends on the total energy density. Inflation naturally drives the universe toward flatness, similar to how the surface of a rapidly expanding balloon appears flatter as it grows. However, inflation is still not fully understood. The exact nature of the field driving it, often called the inflaton, is unknown. It is not part of the standard model of particle physics, and no direct experimental evidence has been found for it. Despite this, inflation remains the leading explanation because it successfully predicts observed features of the cosmic microwave background. Beyond inflation, some models suggest that the universe could be part of a much larger structure known as a multiverse. In these scenarios, inflation does not end everywhere at once. Instead, different regions stop inflating at different times, forming isolated, bubble universes, each potentially with different physical constants and laws. This idea naturally arises from equations in inflationary cosmology and does not require additional assumptions. In some versions of this framework, each bubble universe could have different values of fundamental constants such as particle masses or force strengths. This leads to the idea that what we observe as fine-tuning in our universe may simply be a selection effect. We exist in a region where conditions happen to allow complex structures and life. This connects to the anthropic principle, which states that our observations of the universe are necessarily constrained by the fact that we exist within it. If the universe were fundamentally different in a way that prevented observers from forming, there would be no one to observe it. This does not explain why constants have their values, but it reframes the question in terms of probability across a larger ensemble of universes. At even deeper levels, cosmology intersects with quantum theory in ways that are still not fully understood. The earliest moment of the universe likely requires a theory of quantum gravity, where spacetime itself becomes subject to quantum rules. In such a regime, classical notions of time may not apply at all. Some approaches suggest that time itself could emerge from more fundamental relationships between quantum states rather than existing as a basic dimension. One of the most important open questions is whether the universe had a true beginning or whether the Big Bang represents a transition from a previous state. Some models propose cyclic cosmologies, where the universe undergoes endless cycles of expansion and contraction. Others suggest a quantum tunneling event from a pre-existing vacuum state. In these models, nothing is not absolute emptiness but a quantum state with physical structure. Another possibility is that the universe is self-contained in a way that avoids a true initial boundary. In such models, time behaves more like a geometric dimension rather than a flowing parameter. This idea appears in proposals such as the no-boundary condition, where the universe is finite but without a singular starting edge, similar to how the surface of a sphere has no beginning or end. Observational cosmology continues to test these ideas through increasingly precise measurements of the universe's expansion rate, structure formation, and background radiation. However, many questions remain unresolved, particularly regarding the nature of dark matter, dark energy, and the true mechanism behind inflation. What makes cosmology unique is that it deals with the universe as a whole system. Unlike other sciences that study parts of reality, cosmology attempts to reconstruct the entire history of existence from fundamental physical laws. This makes it both powerful and limited, powerful because it connects everything, but limited because it cannot compare the universe to anything outside itself. As our observational reach improves, we are able to look further back in time, closer to the earliest moments of existence. Yet there is a fundamental barrier. Beyond a certain point, known as the Planck era, our current theories no longer apply. At this scale, quantum fluctuations of spacetime itself are expected to dominate, and a full theory of quantum gravity is required to describe reality. In the end, cosmology suggests that the universe is not static or eternal in its current form, but evolving, dynamic, and deeply connected to the behavior of fundamental physical laws. The structure we observe today, galaxies, stars, planets, and life, is the result of billions of years of expansion, cooling, and self-organization from an initially extreme state. But beneath this entire history lies a deeper question: whether the laws governing this evolution are fixed, emergent, or part of a larger structure that we are only beginning to understand. If cosmology explains how the universe evolved from an extremely hot and dense early state, then the next question goes even deeper. Why do the laws of physics have the form they do at all? Why these constants, these particles, these dimensions? Modern theoretical physics increasingly suggests that what we call laws of nature might not be fixed rules written outside the universe, but emergent patterns arising from deeper mathematical or informational structures. One of the most ambitious attempts to answer this comes from frameworks like string theory, where fundamental particles are not point-like objects but tiny vibrating strings. Each vibration mode corresponds to a different particle, meaning that what we call matter is essentially geometry at a microscopic level. In this view, electrons, quarks, and photons are not separate things, but different expressions of a single underlying entity. String theory naturally requires additional spatial dimensions beyond the familiar three. These extra dimensions are not directly observable because they are thought to be compactified, curled up at extremely small scales. The shape of these hidden dimensions determines the physical constants we observe. In other words, the geometry of unseen space could determine everything from particle masses to force strengths. This leads to a vast landscape of possible universes, each corresponding to a different way of compactifying extra dimensions. Instead of a single unique universe, the theory allows for an enormous number of possible vacuum states, each with different physical laws. This idea connects directly to the concept of a multiverse, where our universe is just one realization among many mathematically possible configurations. In parallel, another approach called loop quantum gravity attempts to quantize spacetime itself. Instead of treating spacetime as continuous, it proposes that space is made of discrete units, like atoms of geometry. These chunks of space are connected in networks, and their relationships define distance and curvature. Time, in this view, emerges from changes in these networks rather than flowing independently. Both approaches suggest a radical idea: spacetime is not fundamental. Instead, it may emerge from more basic structures, whether strings, loops, or something even deeper. This shift is similar to how temperature is not a fundamental property of particles, but emerges from their collective motion. This perspective connects strongly with modern ideas in quantum information theory, where information is treated as the most fundamental building block of reality. In some approaches, spacetime itself emerges from patterns of entanglement between quantum states. The more two systems are entangled, the more connected they are in the emergent geometry. This suggests that geometry is not primary, but derived from relationships. This idea is closely related to the holographic principle, which states that the information contained in a volume of space can be fully described by information on its boundary. If true, this implies that the universe we experience in 3 dimensions could be a projection of lower-dimensional information. The depth of space might be an emergent illusion arising from more fundamental data structures. One of the most powerful examples of this principle appears in the relationship between gravity and quantum field theories. In certain mathematical models, a gravitational system in higher dimensional space is exactly equivalent to a quantum system without gravity in lower dimensions. This duality suggests that gravity itself might not be fundamental, but an emergent phenomenon. If spacetime and gravity are emergent, then the question of what is truly fundamental becomes even more abstract. Some physicists propose that the deepest level of reality may be purely mathematical or informational. In this view, physical existence is not separate from mathematical structure, but identical to it. This idea resembles mathematical universe hypothesis, which suggests that every consistent mathematical structure corresponds to a physical universe. Under such a framework, the laws of physics are not chosen, but simply the properties of the mathematical structure we inhabit. Different mathematical structures would correspond to different possible universes, each internally consistent but fundamentally separate. Our universe would then be one realization among an infinite ensemble of mathematical possibilities. This shifts the question of existence from "why does the universe exist?" to "why this structure rather than another?" In some interpretations, the answer may be that all structures exist, but only some contain observers capable of asking the question. This is where the anthropic principle reappears, not as an explanation, but as a selection effect. Another deep concept comes from statistical mechanics and thermodynamics. Many features of large-scale systems are not determined by exact microstates but by statistical behavior. Temperature, pressure, and entropy are all emergent quantities. Some physicists suggest that spacetime itself might be similar, a large-scale statistical approximation of deeper microscopic degrees of freedom. Entropy plays a particularly important role in this picture. The arrow of time, the fact that time seems to move forward, is closely related to the increase of entropy. The universe began in a state of extremely low entropy, which allowed complexity to develop over time. Why the initial entropy was so low remains one of the biggest mysteries in cosmology. Some theories suggest that time itself may emerge from entanglement or thermodynamic gradients. Instead of being a fundamental axis along which events unfold, time could be a derived concept arising from correlations between states. In such models, the distinction between past and future is not fundamental but statistical. This leads to a very different picture of reality. Instead of a universe evolving in time, there may be a static underlying structure in which time is an emergent perception. In such a framework, all moments might exist simultaneously in a higher dimensional structure, with the flow of time being a feature of conscious experience rather than fundamental physics. At the same time, observational evidence continues to constrain these ideas. Particle accelerators, astrophysical measurements, and cosmological surveys all test predictions of these theories. So far, no direct evidence has confirmed extra dimensions, supersymmetry, or quantum gravity effects, but the mathematical consistency of these frameworks keeps them under active investigation. One of the challenges in modern physics is that many of its deepest theories are difficult to test directly. Energies required to probe Planck-scale physics are far beyond current technological capabilities. As a result, physicists rely on indirect evidence, consistency checks, and cosmological observations to guide theory development. Despite this, the direction of modern theoretical physics is increasingly clear: unification. The goal is not just to describe individual forces, but to find a single underlying framework from which all physical laws emerge. Whether this framework is geometric, quantum informational, or purely mathematical remains unknown. What is becoming increasingly apparent is that the universe may not be composed of things in the traditional sense. Instead, it may be composed of relationships, structures, and information. Matter, space, and time may all be emergent features of a deeper layer of reality that does not resemble anything in everyday experience. In this view, the universe is not a machine built from parts, but a self-consistent structure defined by internal relations. Its evolution is not a process happening within time, but a manifestation of patterns within a deeper system. As these ideas continue to develop, they blur the line between physics and philosophy. Questions about existence, reality, and structure become inseparable from questions about mathematics, information, and logic. The search for a final theory of everything may therefore not only reveal how the universe works, but what it fundamentally is. At the very limit of what physics can currently describe, the question of origin stops being a question about what happened first and becomes a question about whether first even has meaning. Time, as we experience it, assumes a sequence, a beginning, a progression, and a direction. But in modern theoretical physics, especially in quantum gravity and cosmology, that intuitive structure starts to break down. Some models suggest that time may not be fundamental at all, but an emergent property arising from deeper relationships between quantum states. If that is correct, then asking what happened before the universe may be as meaningless as asking what is north of the North Pole. One of the most influential frameworks in this direction is quantum cosmology, where the universe is treated as a quantum system governed by a wave function. Instead of describing particles inside spacetime, these approaches attempt to describe spacetime itself as a quantum object. In this view, the universe does not begin with a classical event like the Big Bang in the usual sense, but with a transition from a quantum state with no classical geometry into one where space and time emerge as stable approximations. The so-called initial singularity may not be a physical point at all, but a sign that classical physics is being pushed beyond its domain of validity. Closely related to this is the no-boundary proposal developed in quantum cosmology, which suggests that the universe may be finite but without boundaries in time or space in the same way a sphere has no edge. On a sphere, you can travel indefinitely without encountering a boundary, even though the surface is finite. Similarly, time in the early universe might behave like a spatial dimension near its origin, smoothing out what would otherwise be a singular beginning. In this framework, the universe is self-contained not because it creates itself, in a temporal sense, but because the notion of a starting point is replaced by a smooth geometric structure. This idea connects naturally to the concept of quantum tunneling at a cosmological scale. In quantum mechanics, particles can cross barriers that would be impossible in classical physics. Some cosmological models extend this idea to the universe itself, suggesting that a universe could emerge from a metastable vacuum state through tunneling. In such scenarios, nothing is not truly absolute nothingness, but a quantum vacuum governed by laws that allow spontaneous transitions into expanding spacetime configurations. This shifts the question from, how did something come from nothing, to, why do these quantum laws exist in the vacuum at all? Inflationary cosmology strengthens this picture by suggesting that once such a universe forms, it can undergo extremely rapid expansion driven by high-energy vacuum states. This inflation smooths out irregularities and creates a nearly uniform large-scale structure, while still preserving microscopic quantum fluctuations. These fluctuations are not noise in a classical sense but encoded variations in energy density that later evolve into galaxies, clusters, and cosmic filaments. Observations of the cosmic microwave background confirm that the early universe was not perfectly uniform, but contained extremely small anisotropies that match inflationary predictions with high precision. However, inflation does not necessarily end the story, it may extend it. Eternal inflation models propose that inflationary expansion continues in some regions of space while ending in others, producing an endless branching structure of bubble universes. Each bubble may have different physical constants depending on how symmetry breaking occurred during its formation. In some bubbles, gravity might be stronger; in others, particles might not form stable atoms at all. This leads to a multiverse picture where our universe is only one realization among a vast ensemble of possibilities. The origin of these possibilities is deeply tied to symmetry. In high-energy conditions near the beginning of cosmic evolution, forces may have been unified in a highly symmetric state. As the universe cooled, this symmetry broke in stages, separating interactions into the distinct forces we observe today. This process is not arbitrary but governed by the structure of quantum field theory. The Higgs field, for example, plays a central role in breaking electroweak symmetry and giving particles mass. Without this transition, the universe would remain in a radically different state with no atoms, chemistry, or complex structures. At even deeper levels, theoretical frameworks like string theory attempt to replace point-like particles with one-dimensional vibrating entities. These vibrations determine particle properties such as mass and charge. Importantly, string theory does not predict a single unique universe but an enormous landscape of possible vacuum states, each corresponding to a different way extra dimensions can be compactified. Estimates of this landscape suggest numbers so large they exceed ordinary physical intuition, implying that the laws of physics we observe may be just one selection among an almost unimaginably vast set of consistent mathematical possibilities. This naturally leads to a shift in perspective. Instead of asking why our universe has the laws it does, we may have to consider that all mathematically consistent laws might be realized somewhere. In such a framework, the distinction between possible and real becomes blurred. This is one of the motivations behind mathematical realism, where mathematical structures are not merely descriptive tools but the underlying substrate of existence itself. Within this broader framework, information becomes increasingly central. Black hole physics shows that information is deeply tied to geometry, entropy, and quantum effects. The entropy of a black hole is proportional to the area of its event horizon, not its volume, suggesting that the fundamental degrees of freedom of spacetime may be encoded on lower dimensional boundaries. This leads to the holographic principle, which proposes that the entire contents of a region of space can be described by information stored on its boundary surface. If this principle is correct, then the three-dimensional universe we experience could be a projection of underlying two-dimensional information. This does not mean the universe is an illusion, but that its most fundamental description may be encoded in a radically different form than our sensory experience suggests. In such a case, geometry itself would be emergent, arising from patterns of entanglement and informational relationships rather than existing as a primary entity. Entanglement plays a crucial role here. In quantum mechanics, entangled particles share a joint state such that the measurement of one immediately determines the state of the other, regardless of distance. Experiments repeatedly confirm this non-local behavior, ruling out classical explanations based on hidden local variables. Some modern approaches suggest that space itself may emerge from entanglement networks. In this view, distance is not fundamental but derived from how strongly quantum systems are correlated. Highly entangled systems appear close, while weakly entangled systems appear far apart. This idea radically reframes cosmology. Instead of a universe made of matter moving through space, we may have a universe made of information relationships generating the appearance of space, time, and matter. Gravity, in some emergent models, is not a fundamental force but a consequence of entropy gradients or information redistribution. Matter curves space not because space is a pre-existing stage, but because geometry itself is a macroscopic expression of underlying informational structure. Dark matter and dark energy remain major unknowns in this picture. Their existence is inferred through gravitational effects and cosmic expansion, but their nature is still unexplained. Dark matter appears to stabilize galaxies, while dark energy drives accelerated expansion. Together, they dominate the energy content of the universe, yet remain invisible to direct detection. Some speculative theories suggest they could be manifestations of deeper geometric properties of spacetime or residual effects of higher dimensional physics. When all of these ideas are considered together, a consistent but highly abstract picture begins to form. The universe may not be a single object with a defined origin in time, but a self-consistent system of physical laws that generate space, time, matter, and energy as emergent phenomena. What we call existence may be the stable solution of deeper mathematical and quantum constraints that do not themselves require an external cause. Even so, the most fundamental question remains unresolved. Why do these laws exist in the first place, rather than different ones, or none at all? Physics can describe how structure emerges, how complexity evolves, and how universes may form under certain conditions, but it does not yet explain why there is a framework capable of producing conditions at all. That question sits at the boundary between physics, mathematics, and philosophy. And so the final picture is not one of closure, but of expansion. The deeper we go, the less the universe resembles a simple object with a beginning, and the more it resembles an ongoing process, one that continuously generates structure, possibility, and complexity through laws that we are still only beginning to understand.